Ladies and gentlemen, class recording has started. That's on purpose too, by the way. All right, yesterday we got started in on section 6.2, and like the title suggests, 6.2 deals with the relationship between work and energy. And we started off with those two statements explaining the relationship between work and energy. When you do work on an object, you change its energy. And similarly, energy has the capacity to do work on an object, which is great unless you really don't know what energy means. In the first section, we talked about that work depends on force and distance, right? But here now we know that work changes energy, but we don't really know what energy was. So yesterday, I gave you this definition for energy. And I told you that that definition we are going to basically carry from now until the end of the year, because energy shows up in almost every application that we hit from this point forward. So we will see how this definition relates and applies to a lot of different situations. The first type of energy that we talked about yesterday was kinetic energy. Energy is energy of motion. By virtue of the fact that an object is moving, it has the ability to move or change other stuff. The amount of kinetic energy that an object has depends on two factors, its mass and its velocity. And we spent a good time yesterday talking how those two things relate to or determine the kinetic energy. That kinetic energy increases linearly with mass, but with the square of velocity. And that will be important as we go along here a little bit more today. Towards the end of class, we introduced and derived the work energy theorem. The total work done on an object equals the change in its kinetic energy. Mathematically, we summarize that with this expression, right? W is equal to delta KE, right? Where W stands for work, delta the change, right? KE is kinetic energy. But we said that that comes from this derivation where we put equations together that we had been introduced to previously, putting them all together to see how this relationship works. This equation tells us exactly the same thing as this equation. It both shows us that work is equal to the change in kinetic energy, but this equation, more detailed, showing us the relationship between force and distance and how that affects the work, but then also the individual factors that contribute to the kinetic energy. So this equation and this equation are exactly the same one, just we might use it for different applications in different settings. Good? Okay. Let's take a look here at conceptual example 6.9, how much work is required. So it says, to accelerate a certain car from rest to the speed v requires the work w. Is the work required to accelerate the car from v to 2v equal to w, 2w, 3w, or 4w? All right, so this question, obviously this is like a multiple choice question just waiting to happen, okay? But it's also very representative of the kind of questions that show up on standardized tests. Not that you guys are taking an AP test in physics, obviously, but this is the kind of question that shows up in multiple choice questions all the time. No numbers, just showing us the factors and how they're related to how the different factors relate to each other. So here's what I'm going to do to help you guys answer this question. I'm going to make us a chart. A chart for each portion of this car's trip. One for its starting position. Second column for the second or the middle information that it gave us, and then third column for the ending position of this trip. So it says to accelerate a certain car from rest to speed v. One of the rows in this chart I'm going to label as v. That's going to be our velocity. If it says that this cart accelerates from rest, what is the initial velocity of that cart? So the velocity here has to be 0. It says it then accelerates to a speed v. It doesn't tell us actually what that speed is, but we know now that this car is going that fast at that second picture in the example. Good with that so far? It then says that doing that requires the work W. Remember, according to the work-energy theorem, work changes the energy that is involved, or changes the energy of an object. Meaning, we can't necessarily talk about the work at this point, or at this point, or at this point, but we have to talk about the work going from this point to this point. Does that make sense? Because work deals with changing the kinetic energy of an object. So, it tells us that this first trip requires a work that is equal to the value W. Again, we don't know what it is, but we do know that we're going to call it value W. It's asking us then, we're accelerating the car from V to 2V, meaning the third picture here, while we don't know exactly how fast that car is going, we do know that it's twice as fast as the previous picture. And then it's asking us how much work do we need to do that? We make sense of the layout so far. We did. Okay. In looking at our formulas for work, do any of our formulas, right? One's right here. W equals F times T, right? I should write that up here. Because people on the recording can't see it. We learned that expression back in 6.1. We learned this expression in 6.2. According to either of those equations, is there a relationship between work and velocity? Does velocity show up in either one of those equations? It doesn't. But there is something that we can use as an intermediary taking us from velocity to work. And that thing that we can use is kinetic energy. Because kinetic energy depends on velocity, but kinetic energy is also changed when work is done. In the first picture, if the velocity of the car is 0, what has to be true about its kinetic energy? It has to be 0 as well. In the second picture, while it doesn't give us a mass and it doesn't give us an actual velocity, we can't calculate the exact amount of kinetic energy. That's weird. I don't know. It does sound like a train, but I really don't think it is a train. This will be a recording to watch. Yeah. Get one more in, you know. Maybe they were just mulching up like the last remaining leaves. What? Yeah. Well, I guess. Yeah. Actually, the leaves are actually really good, like they decompose and fertilize the grass, but whatever. So. All right, sorry for that delay. All right, second picture. It didn't give us an actual mass, it didn't give us an actual velocity, so we can't calculate the actual kinetic energy, but now that this car is moving, we know that it does have kinetic energy. While we don't know how much, so we're just going to call it KE. We know it has kinetic energy, but we don't know how much. Yesterday, we spent a good amount of time talking about the relationship between velocity and kinetic energy, and how, as the velocity changes, the kinetic energy changes. But we said that kinetic energy depends not on the velocity, but on the square of velocity. Meaning, if we go from v to 2v, we're doubling our velocity. What does that do to our kinetic energy? How much more kinetic energy will we have now? 4 times. Because kinetic energy depends on the square of the velocity. All right, that being said, now we have information that we need in order to answer this question. We learned previously in 6.2 that work is responsible for the change in the kinetic energy. How much does kinetic energy change going from here to here? By a factor of what? By a factor of 3, yes. Going from KE to 4KE is an increase of 3, right? That makes sense? If it took us work W to go from 0 to 1, going from 1 to 4, requires 3W worth of work. Does that make sense? Yes, no, maybe? Right. We're looking at that relationship and how velocity affects the kinetic energy, right? It affects it by the square of the velocity, but going from this initial amount of kinetic energy to this amount of kinetic energy is an increase in 3. That's why 3W is the amount of work that needs to be done. Okay? Good? All right. Let's step back into the realm of a little bit more comfort that you guys have. Let's put some numbers on this. Okay? So, quick example 6.6. What's the work? Again, I would consider this to be pretty straightforward, so instead of just walking you guys through it, we'll just talk about it as I go along, right? How much work is required for a 74 kilogram sprinter to accelerate from rest to a speed of 2.2 meters per second? How much work means we're looking for the amount of work, right? $74 kilogram sprinter, that means the mass is 74 kilograms. From rest, VI 0 to a speed of 2.2. Okay? Good with those? All right. It's asking us to calculate the work. And we learned earlier, right, in section 6.1, that we can calculate the amount of work on an object if we know force and distance. But they didn't give us force and distance in this problem. But we just learned in section 6.2 that we can also calculate the amount of work on an object if we know its change in its kinetic energy. You don't necessarily have to write all of these steps every time you solve this problem, but just to follow the pattern. When we calculate the change in anything, or delta anything, right, it's always final minus initial. What does it tell us about the initial velocity in this problem? Or what is the initial velocity of this problem? 0. And if the initial velocity is 0, is there any kinetic energy at the beginning of this problem? Kinetic energy depends on movement. So that whole term then would become 0 because there is no kinetic energy at the beginning. So then we would expand this out. We learned that the formula for kinetic energy is 1/2 mv squared. If we're specifically dealing with the final kinetic energy in this problem, we should use the final velocity. We start plugging in things we know. And if I remember correctly, 1709? Wait, right there. What? Wait. Did you square your 2.2? Yeah, we're good. My bad. The next one is a number in the thousands. 179.0 something, right? Yeah. Alright. So 2 things to finish this off. 2 sig digs in the mass, 2 sig digs in this velocity. So we should round our answer to 180. And then kilograms times meters squared. Kilograms times meters squared over seconds squared. That combination gives us joules, because work has to be in joules. Okay. Good there? All right. The next problem that I want to do with you guys, the 2 examples that are in your packet are examples from the chapter, but looking at them now is like, I don't know if these really are where I want us to take these. I thought they were pretty easy, kind of plug and chug problems. So I went into the book and got one of your homework problems. And this is on page 221 of your book. If you want to, just in your packet, like in the bottom right-hand corner of that page that we're working on, you can just kind of do it in that space right there if you want to keep it all together, okay? Or on page 5 of your packet, there is a big open space down at the bottom. There's a little bit of room there. But this problem is from page 221 of your book. It's number 92. Is that the right page, at least 221? Yeah. All right, so it says, a 1,100 kilogram car is coasting on a horizontal road with a speed of 19 meters per second. After passing over an unpaved sandy stretch 32 meters long, the car's speed has decreased to 12 meters per second. So, part A says, was the net work done on the car positive, negative, or 0? This one doesn't really require us to do any calculations if we reason properly. We learned in section 6.2 that the amount of work done on an object equals the change in its kinetic energy. And we know that the change in the kinetic energy depends on final minus initial, KE final minus KE initial. What do we see about the final velocity versus the initial velocity in this problem? Final velocity is smaller than initial velocity, meaning the final kinetic energy will be less than the initial kinetic energy. If we plug that into this formula, if we have a smaller final minus a greater initial, work has to come out with what sign? It has to be negative, right? So in this case here, we have done negative work, or the sandy stretch of unpaved road has done negative work on the car. Because what did it do to its kinetic energy? It decreased the kinetic energy. So, using our work energy theorem, anytime we have an increase in kinetic energy, we're going to do positive work on an object. Anytime we have a decrease in kinetic energy, we're going to do negative work. Good there? The second part, part B, find the magnitude of the average net force. So we're looking for the force that acted on this car as it went over this sandy, uneven patch, or unpaved patch. All right. Good with that information. See where it all came from? We learned that the amount of work done on an object is equal to its change in its kinetic energy, and that to calculate the change in the kinetic energy, we need to know KE final minus KE initial. Going back to the derivation of that relationship, we ended up here. The left-hand side of this equation is F times D. That's how we calculate the work. The right-hand side of that equation is the change in the kinetic energy, calculating the kinetic energy of each individual spot separately. All right? I think if you take a look at what we were given in the problem and this equation, right? Oh, sorry, one point. The work that we calculate this way is no different than the work we calculate this way. It's a different way of calculating it, but we're talking about the same work in both of these instances. So we can set this equal to this, which is what we've done right here. Okay? So I think, right, keep that in mind, that even though we introduced work in the first section as F times D, and then we introduced in the second section work is equal to delta KE, right? It's the same work. So we can set those equal to each other to solve for what we need to solve for. So I think that you'll find that in the information that we were given in the problem, you should be able to calculate the amount of force that was acting on that car. Okay? Yeah, we'll get there. That's why to give people a chance to kind of run it through here. All right, let's take a couple more seconds here, finish this up, then we'll talk about our final answer. If you're not getting that number, let me know. Make sure you square your velocities. That's always the one thing. So we said that we could set them equal to each other, or basically this equation that we used earlier, which I think shows up on page 2 of your packet, that's setting them equal to each other, right? That's setting the two expressions that we introduced for work equal to each other. And I believe we have everything in this equation except for the force, which then means we can then solve for the force using that equation. So again, make sure when you're doing your calculations, you square your velocities. That's always the one. That's a big point where people mess up with the calculation. All right. So, a couple of things as far as getting our final answer. 1, 2 sig digs, 2 sig digs, 2 sig digs, 2 sig digs. So we should round our answer to 2 significant digits. 2. Because we're solving for a force, what unit should it have? We're solving for a force, it should be newtons. Okay? 3, what did the question actually ask us for? The magnitude of the force. So does it have to be negative? No. Right? If it's a magnitude, it's just a number. It comes out negative because if we're slowing down, that's going to require a negative force, right? But in this question, it just asks us for the magnitude. Right, go ahead. Technically, magnitudes can't be negative, right? 'Cause it's just how much of something, right? Although on a test, I would probably say find the force. So in that case, the negative would be appropriate.
But if it's just the magnitude, isn't it just putting a number mean that's positive?
No, because you're asking for the magnitude. Magnitude can never be negative, right? If you're asking for the magnitude of the force, you're really only asking for half of the force, because the force requires magnitude and direction, right? You're really not asking for the whole thing. Does that make sense?
Yeah, but like,
It's like,
just putting a negative number is putting the direction.
right, but that's important for force because force is a vector quantity. It's the difference between, here, see if this works. Okay, ready? That versus that, right? If we make it a vector quantity, it needs to have some kind of direction. But if we're just talking about F, that's just the magnitude of that force. So, all right, good there? Okay, let's transition. Next page, which might not be the next page if you were doing it on page 5, it's the previous page, but. All right, so here's a picture of a lady lifting a bowling ball from the floor and putting it on a shelf. Maybe not the smartest idea in the world, but, right? So, in order to lift the bowling ball from the ground to the shelf, she needs to apply a force to that bowling ball, yes? Okay. And she's applying the force, right? I should use that as red because it's red in this picture. So, she has applied a force, we'll call it applied force, right? In lifting that bowling ball from the ground to the shelf. In the course of applying that force, she has moved the bowling ball from the ground to the shelf a certain distance. Has she applied force? has the object moved a certain distance because of her force? According to our definition, has she done work on this object? Yes. However, we just discussed that this is one way to calculate the amount of work done. That's the other way to calculate the amount of work done. Before the bowling ball started moving, before she picked up the bowling ball, it wasn't moving. After she places it on the shelf, it's not moving. Meaning, was there any change in the kinetic energy? If it started at 0 velocity and ended at 0 velocity, it would appear that delta KE is 0. But here, we said she did work. But here is not showing up as work. That can't be. So what happened, right? Was it work or was it not work? And the answer was, it was work, but it wasn't kinetic energy. That leads us to potential energy. While kinetic energy is energy of motion, by virtue of the fact that something is moving, it has the ability to move or change other things. Potential energy is energy of position. While we're not changing an object's motion and its ability to move or change other objects, we are changing its position. And that then allows it to potentially move or change other objects. Potential energy of an object is determined by the amount of work required to move it from one location to another. So with potential energy, right, we can't use delta KE, but we can look at the amount of change in different forms of energy to determine how much work was done. Or, if we know how much work was done, we can use that to calculate the change in the other kinds of energy, namely those being potential energy. Okay? Good there? Tomorrow, we will see how potential energy turns out being equal to mgh, or the mass of an object, times the acceleration of gravity, times the height that we move it. And we'll also learn about a different form of potential energy called elastic potential energy, which again is a position thing, but instead of dealing with gravity, we're dealing with elasticy things like rubber bands and bungee cords and things like that. Okay? There is homework on the calendar for tonight, but you might save it until tomorrow when we finish up talking about potential energy. And then you'll have all the formulas and we can go from there. Okay? So tomorrow, we'll finish up potential energy, maybe look at a couple more concepts. We're back on lab on Thursday.